Hello everybody. In this video, I'm going to introduce a topic which appear in nearly in every HKDSE exam, paper 2. Usually, this question appear in question 17 or 18 of paper 2 every year. It is about area of ratio of some triangles or parallelogram or some rectilinear figures. Now, for example, you can see in the figure, we have a figure A, B, C, D, E, and suppose the area of triangle ABE here is 4 cm square, and we know that the area of triangle DEC is 9 cm square. So, how to find the area of the triangle EBC? Okay, we are going to introduce two useful tools to handle this kind of problem. This is a theorem 1. Suppose triangle ABC here is similar to triangle PQR. Then of course you have learned in Form 3 that area of triangle ABC, the ratio to the area of triangle PQR will be the ratio of AB to PQ square, or BC to QR square, or AC to PR square. In other words, area of triangles will be of similar triangles especially, will be the ratio of the length of the corresponding sides in this pair of similar triangle, but with square. This is theorem 1. And another useful tool is theorem 2, which is a simple fact, but you may not be realized in usual problem. Now, in triangle ABC and PQR, they are not similar. However, they have same height. That is this one, the height of triangle ABC, and the height of triangle here, PQR, are the same. Then, the area of triangle ABC, the ratio to the area of triangle PQR will be the ratio of the base BC to QR. And note that you need not take square in this case. Because the two triangles are not similar, you cannot use theorem 1. But one fact is that we know that they are of same height. And therefore, the ratio of the area will be the ratio of the base. Similarly, suppose I have two other triangles, ABC and PQR. This time, I know that the length of their base are the same, but they are of different heights. For example, in triangle ABC, the height is h1. In triangle PQR, the height is h2. In this case, these two triangles may not be similar, but the area of the triangles can be obtained by just taking the height of the ratio of their height, h1 to h2. No need to take square. Okay. So, repeat once again. If area for the ratio of area of triangle with same height will be the ratio of their bases. On the other hand, the ratio of area of triangles with same base will be the ratio of their height. Let us consider the following example. In the figure, we have a 5-side polygon ABCDE with AB here is parallel to DC. Now, since AB is parallel to DC, we can prove or see easily that triangle AEB, this one, is similar to triangle CED. Because they are similar, so area of ABE, the ratio of area of AEB to CED will be the ratio of the length of any corresponding size and then taking square. Say, for example, AE to CE and then square. On the other hand, when we look at the triangle AE and AEB and ECB, suppose we rotate the figure a little bit and you get a figure like this, because triangle, the height of triangle AB, AEB is this. At the same time, the area of triangle CEB, this one, CEB, will also be the same height. Therefore, the area of triangle AEB to area of triangle CEB will be the ratio of their bases AE to CE. Example 1, which comes from a question in 2013 Hong Kong Mathematics Olympic HKMO. Now we have a trapezium ABCD in the figure where AB is 3, CD is 5, and the diagonal AC and BD meets at O. We know that the triangle of the area of triangle AOB is 27. Find the area of the whole trapezium. Okay, now since ABCD is a trapezium, we know that AB here is parallel to CD by the definition of trapezium. AB is parallel to CD. Therefore, we can prove easily that triangle AOB, this one, is similar to COD, this one. AOB similar to COD. And therefore, according to the question, AB is 3, CD is 5. Area of triangle AOB, the ratio to the area of triangle COD will be the ratio of the length corresponding size and then square. So we have substituting the value. Area of triangle AOB 27. Area of triangle COD unknown. AB is 3, CD is 5. So we have this equation. Taking square, 3 square will be 9, 5 square will be 25. Cross multiplying, we know that triangle COD will be of area 75. All right, 75. So we know that this is 75 now. All right, 75. Okay, just mark it down. Now, second step, I consider this time these two triangles, AOB and AOD. Now, take a look at it. In this figure, we know that triangle AOB is this one. AOB is similar to COD. So, the ratio of corresponding size must be the same. If the ratio is here to here is 3 to 5, then the ratio for here to here, OB and OD, must be 3 to 5 also. 3 to 5 again. The length may not be exactly 3 cm and 5 cm, but the ratio must be 3 to 5. 3 to 5, the ratio. Now, go to this figure. The ratio of 3 to 5, this is 27. Now, imagine you are looking at the triangle in this direction. Looking at this, you can see triangle ABO, this one, and triangle ADO, this one, are of the same height. This is the height. Therefore, according to theorem 2, area of triangle ABO to area of triangle ADO must be the ratio of their bases OB divided by OD, but no need to take square. Substitute the value again. Area of triangle ABO is 27. OB 3, OD 5. Area of triangle ADO unknown. Now solving equation, cross multiplying, you will see that area of triangle ADO is now 45. We know that it is 45. So this is 45. We now know that this is 45. This is 75. Right? We only need to find the last part, OBC, and then add all the areas up will be the area of the whole trapezium. And this time, we concentrate on triangle AOB and COB. Again, by considering this pair of similar triangles, OAB and OCD, you will get the ratio of size AO to OC 3 to 5 again. Now, because they are of the same height, triangle AOB and COB are of same height, so their area, the ratio of their area, again, will be the ratio of their bases. Therefore, area of triangle ABO to area of triangle ACO, the ratio will be OB to OC. Note that no square here. Substitute the value again into the expressions. 27 3/5. Cross multiplying. We know that area of AC triangle AOCB will be this one will be 45. 45 again. 45. Finally, area of the trapezium ABCD will be the sum of these four, which is 129, and we'll get the final answer. Now, I have a simple note here. For any trapezium with AB parallel to CD, and we draw two diagonals, AC and BD, then this area, OAD, will always be the same as this area, OBC. Example 2. In this figure, ABCD is a parallelogram, and we know that the ratio of the length of DF to FC is 3 to 1. Suppose the area of the whole parallelogram is 48. Find the area of this part, ADFE, this part. Okay, how to find this area? Look at the figure. The two lines divide the parallelogram into 4 parts. To simplify our calculation, we may always let the smallest part, the area, to be K. To simplify our calculation, I let this one to be K. Now, because ABCD is a parallelogram, so these two lines must be parallel, right? And therefore, you can prove that triangle AEB, this one, is similar to CEF, this one. And we know that the opposite side of a parallelogram must be the same. So the length of AB should be the same as the length of DC. If the ratio is 3 to 1 here, this part is 1. AB must be 3 plus 1, which is 4 here. The ratio of AB to FC must be 4 to 1. So we have this. The ratio is 4 to 1 here. And now, because the area of triangle CEF is K and the ratio is 1 to 4, so using theorem 1, these two triangles are similar. The ratio of area should be the ratio of corresponding length square. Substitute the value. Area of triangle AEB, this one is unknown, but triangle CEF is K, and the ratio is 4 to 1 square. Taking square, you have 16, and area of triangle AEB must be 16K. This one. Now, this is 16K. The area. This is K. This is 16K. Now, we look at the figure, this part. ABC. In this area, these two triangles, you can see that the ratio is 4 to 1. Again, since these two triangles, ABE and CFE, are similar, and the ratio here is 1 to 4, these two ratios must be 1 to 4 also. The ratio should be 1 to 4 again. And we know that the area of ABE is 16K by the previous part. And these two triangles are not similar. However, they are of the same height. The height here, same height. Therefore, the ratio of area of triangle ABE to that of CBE must be the ratio of their bases, 4 to 1. Substitute the value. 16K divided by area of triangle CBE will be 4 to 1. No square here. Be careful. Cross multiplying. We know that the area of CBE will be 4K. This one will be 4K. So go back to our figure. This one will be 4K. Right? 4K. Now, we have the figure ABC. The area of ABC is totally 20K, right? But note that the figure, the area of triangle ABC is actually half of the area of the whole parallelogram. ABCD, 48. So we know that area of triangle ABC must be half of 48, which is 24. 24. Therefore, 20K equals 24, and we know that the area of the value of K must be 1.2. Now, go back to the figure. CAD is triangle. CAD must be again half of the area of the parallelogram, which is 24. And this small triangle, the area is K. So K is 1.2 by the previous part. Area of the region we want to find, ABFE plus 1.2 will be 24, half of the parallelogram. And therefore, area of ABFE must be 22.8. And we have solved the problem. And example 3. In the figure, we want to find the area of triangle BCE. We know that AB is parallel to BC here. And the area of triangle ABE and DEC are 4 cm square and 9 cm square respectively. Okay, we want to solve the problem step by step. Since these two lines are parallel, then we can see that triangle AEB is similar to triangle CED. Similar to triangle CED. These two are similar. Therefore, we know that the ratio of the areas must be the same as the ratio of the corresponding sides AE and CE. Therefore, I take AE and CE. area is 4 and 9. 4 divided by 9 will be AE over CE squared. Taking square root, the ratio of AE to CE must be 2 to 3. AE to CE 3. Of course, the actual length of AE and CE may not be 2 cm and 3 cm, but the ratio must be 2 to 3 here. Ratio 2 to 3. Using theorem 1, area is 4 to 9. Taking square root, ratio of length of the size is 2 to 3. Now, we move on to the next figure. The area of AEB is 4. And from previous part, we know that the ratio is 2 to 3. 2 to 3 here. The ratio is 2 to 3. Therefore, these two triangles, AEB and CEB, are not similar, but we know that they are of the same height here. So, the ratio of the area of these two triangles must be the ratio of the bases, 2 to 3. 4 divided by area of triangle CED will be 2 to 3, and therefore substitute the value. Area of triangle CEB, the one we want to find, this one, will be 6 cm squared. And so we have solved the problem. Example 4, which comes from 1999 HKCE Maths MC question. In the figure, ABCD is a rectangle. M is the midpoint. Look the word midpoint here. That is, the ratio of BM to MC is 1 to 1. MD and AC intersect at N. Now I want to find area of NCD, this one, to area of ABMN, this quadrilateral. Okay, so the basic principle, we always trying to let K to be the area of the smallest part of in the figure, and for simplicity, we let area of triangle CMN to be K. Now, we know that M is the midpoint of BC, and of course, the opposite side of a rectangle must be the same. Therefore, if this is 1 to 1, the ratio, BM to MC is 1 to 1, the ratio of MC to AD must be, of course, 1 to 2, right? M is the midpoint, MC is half of BC, and BC equals AD. Therefore, the ratio of MC to AD is 1 to 2. Now, we can see that these two triangles, ABN and ADN and CMN, are similar, and the ratio of MC to AD is 1 to 2. So, area of triangle ADN, the ratio to area of triangle CNM will be AD, the ratio of AD to CM square, according to theorem 1. So, substitute all the values in the figure. Area of triangle AND divided by K will be 2 to 1 square. Cross multiplying, we know that AND now is 4K. Alright, 4K. So, go back to the figure. This is 4K. Okay, 4K. And then, we move on to the next part. In this figure, we move on to this half of the rectangle ADC. In this figure, the ratio is 2 to 1 because we have proved that ADN and CMN are similar. The ratio here is 2 to 1. 2 to 1. Then this ratio must be 2 to 1 also. 2 to 1. Therefore, ratio is 2 to 1. The area here is 4K. We have shown in the first part. So this is 4K. And the ratio of AN to NC is 2 to 1. Note that in these two triangles, ADN and CDN, they are not similar, but they have same height here. Same height. Therefore, the area of AD, AND, and CND must be the ratio of their bases, 2 to 1. And we know that this area is 4K. 4K divided by area of triangle CND will be 2 to 1. Cross multiplying, area of triangle CND will be 2K. This part will be 2K. Alright. Now go back to the original figure. This part will be 2K. Alright. Now don't forget, we want to find the area of NCD to this quadrilateral ABMN. We know that triangle NCD is 2K now. What we should do is to find the area of triangle quadrilateral ANMB in terms of K. Don't worry, because we know that this is 4K, this is 2K. So when you add up, half of the rectangle must be 6K. And automatically, we know that ABMN will be 6K minus K, which is 5K. Now, look at the figure here. We have this figure. Altogether, ADC will be 6K. This is K. So, this remaining part must be 5K. Right? Because this half ACD and this half ACB are the same. 6K, this part should be 6K. And therefore, finally, our answer for the whole problem, the ratio of this one and this one will be 2K to 5K. When you cancel the unknown K, the ratio is 2 to 5. So that we have finished the problem.